You're welcome back. This is Mr. Hyper taking you through phase Equilibria. This is our lesson number 6. Previously we looked at the calculations that involve Rod's law, and I'm happy that some viewers were able to get to me about the answers they got. But this time around, I'm taking you through the phase diagrams for ideal solution. Remember, we say that a phase diagram is a plot showing conditions of temperature and pressure under which different physical states of substances are stable or are in equilibrium. So, if we say vapor pressure compression diagram for an ideal solution, we are going to look at the fact that in a liquid, the fact that we are looking at ideal solutions. So I'm going to say that in a liquid mixture, that behaves ideally, the partial vapor pressure of each component proportional to its mole fraction. So we are going to consider, I'm going to explain much about that. We're going to consider an ideal solution which is composed of liquids A and B. Now, we are saying that in a liquid mixture that behaves ideally, the partial vapor pressure of each component is proportional to its mole fraction. The partial vapor pressure of each component is proportional to its mole fraction. So if we consider an ideal solution of liquids A and B, okay, we are going to have zero, one. Instead of mole fraction, sometimes you can find composition by mass. So here we shall have mole fraction of B. And it means that now, from left to right, that is mole fraction of B. Meaning if you put here a 0 to 1, this side will be mole fraction of A. So from here to here, mole fraction of B. But if here is 1 and here is 0, then that is mole fraction of A. So that is the mole fraction. And here we shall have vapor pressure. All right. Which I can see in pascals. Now, I'm going to assume that my vapor pressure assuming that I have that. and that, then and that. These are straight lines. So if I call this one the partial pressure of pure air, and this one partial pressure of pure B, right? So it means that on this line, from 0 to partial pressure of B, that one will give us the partial vapor pressure of B, which is equals to mole fraction of B times its partial pressure in pure state. This one, partial pressure of A equaling to mole fraction of A times partial pressure of A in pure state. All right, and this is what I'm having. Then here I'll have P total. And this total is equals to partial pressure of A as partial pressure of B. Okay. So here shall have liquid, and then we shall have vapor. So this is the vapor pressure composition curve for an ideal solution. And we are going to explain what each line represents. We're going to explain the representation of each line, and then we see the importance of this very line. So at this point, I want you to know at this point, since we are saying that mole fraction of B, it means that the mole fraction of B here is 0, and here the mole fraction of B is 1, okay? Then here, the mole fraction of A is 1, the mole fraction of B, sorry, the mole fraction of A is 0. From this side, if you move from this side to this side and you say that's the mole fraction of B, then the opposite is the mole fraction of A. Now, this is the liquid phase because you have to show all the regions. This is the liquid phase, and this is the vapor phase. What does it mean? From this diagram, okay, we can really see that from this diagram, the vapor pressure of A is higher than the vapor pressure of B. In other words, from this diagram, you can conclude that liquid A is more volatile. If the vapor pressure is high, then it means that it is more volatile than B, simply because at any given composition, liquid A exerts a high vapor pressure than B. In other words, it produces a lot of vapor. Let me first talk about the presentation of these lines. In short, PA represents the vapor pressure of pure air. Vapor pressure of pure air. All right. Then PB represents the vapor pressure of pure B. Then line PB okay. Line PB shows the variation. It shows the variation of partial vapor pressure of B with the composition. You should be able to know what this line stands for. If we say line PB, it shows the variation of partial vapor pressure of B with the composition or mole fraction with composition. So we are talking about B specifically, partial vapor pressure of B with the composition. Then line PA shows variation of partial vapor pressure of A with the composition. All right. Then for that line P total, it shows the variation of total vapor pressure of the solution with the composition. The solution with the composition. Now, another thing which you should note from the diagram is that PA is higher than PB. Can see if you had plotted values, this is higher than this, simply showing that A, component A, is more volatile than component B. It escapes to vapor phase easily than component B. So that is basically what these lines present, the interpretation of the graph. Another thing that you should note from this, you should know that the partial vapor pressure of each component increases with the increase in its composition in the liquid mixture at any given composition. In other words, at any given composition, the total vapor pressure is equal to the sum of partial vapor pressures of the two components at that particular composition. But the main important thing you should know is that the vapor pressure of each component increases with the increase in its composition in the liquid mixture, meaning that when the composition of component A increases, its vapor pressure increases. If the composition of component B increases, then the partial vapor pressure of B also increases. Now, this vapor pressure composition diagram can help us predict very well the shape of the boiling point composition diagram, whereby you can easily know that when a component is having a high vapor pressure or a higher partial vapor pressure, it means that it easily escapes into the vapor phase, and therefore its boiling point is lower. So here in the boiling point composition diagram, we would expect the boiling point of component A to be lower than that of B, because if it easily escapes into vapor, or if it's having a higher vapor pressure, then it means that it boiled at low temperatures. It requires low temperature to escape the vapor phase. Now, my point I'm trying to emphasize is that we can use vapor pressure composition diagrams to predict the boiling point composition diagrams as shown below. So allow me to say that the vapor pressure composition diagrams we call it diagram can be used to predict the shape of the boiling point composition diagram of the boiling point composition diagram. Okay, let me say as shown below. Meaning in an exam, they can first give you the vapor pressure values and mole fraction. You plot them. Then after plotting them, they say that sketch a boiling point composition diagram. And that is what we are going to see. How do we sketch a boiling point composition diagram? Now, with the boiling point now, we shall not use vapor pressure, but temperature. So we shall have temperature axis this time round, because we're looking at boiling point composition diagram. So we have temperature in degrees Celsius, and then this side still we shall keep with composition, or what we can say the mole fraction. This is B, mole fraction of B. Now, we said that previously in the vapor pressure composition diagram, the partial pressure of A was high, meaning that its boiling point this time would be lower. And the boiling point of B, which had low vapor pressure, would be higher. So allow me to say that this point represents the boiling point of pure B. Since it had lower vapor pressure, it means that it boils at a higher temperature. So this is boiling point of pure air. So we are going to have our vapor pressure composition diagram drawn as this. So they can give you, rather this is our boiling point composition diagram. So they can give you values of vapor pressure, and in mole fraction, you plot them, you get the other previous composition diagram of vapor pressure. Then if they say you use it to predict the boiling point composition diagram, I would expect you to come up with this. And they normally say, draw a well-labeled. So to label this, you need to first show me that this is vapor phase this time. Because if A boils, you go to vapor, so this is vapor phase. And the same applies if B boils. And this one now will be our liquid phase. Allow me bring in the equilibrium. Before the equilibrium, this one here, this curve is the vapor composition curve. And this one is the liquid composition curve. Then we shall also have that. Let me call this one Y. Let me call this one X. In some books, they just call it, they just say liquid and vapor in equilibrium at that very point, okay? But still it is okay. One can say liquid vapor in equilibrium, okay? But I will also bring it in another perspective. However, as I've said, one can put liquid, double alloys, vapor, meaning liquid and vapor are in equilibrium. Now, at this point, can have the mole fraction of B. So if 0 to 1 is for B, then that is the mole fraction of B. If 1 to 0 is going to this side, then that is mole fraction of A, but you can present using one of them. Now, this diagram shows that an increase in the composition of less volatile component results into increasing in boiling point of the mixture. An increase in the composition of B, which was less volatile, even by me having its boiling point high, it means that it was less volatile. So an increase in composition of less volatile component B results into an increase in the boiling point of the mixture. Similarly, an increase in the composition. Now, if we are going this side, an increase in composition, okay, let me say like this. An increase in, now this is for A. An increase in composition of A, which was more volatile, results into the decrease in the boiling point of the mixture. So an increase in composition of B, which was less volatile, increases the boiling point. Whereas an increase in the more volatile decreases the boiling point of the mixture. In that, the moment the mixture starts boiling and introducing a more volatile component, or the component that easily escapes to vapor, the boiling point of the mixture decreases. So now, that one is very important to note. The diagram shows, one can ask you the deductions from the diagram. You should be able to tell me that an increase in the composition of a more volatile component results into an increase in the boiling point of the mixture, while an increase in the less volatile component results into a decrease in the boiling point of the mixture. Okay, that is, more volatile is from right to left, while less volatile is from left to right. Okay, now, when a liquid mixture at any given composition is heated, we are going to find that the vapor is obtained, and that vapor obtained is more volatile, is richer in a more volatile component. Let me note that when a liquid mixture of any composition is heated, the vapor obtained is richer in more volatile component all right? the tie line, we call the tie line XY. This is what we call the tie line, okay? Shows liquid vapor equilibrium. So that's why I was saying that one can show it as the liquid vapor equilibrium. Shows liquid vapor equilibrium established when a liquid mixture of composition XB is heated. It gives a vapor of composition Y, which is richer in more volatile component A. When we heat a liquid mixture of any composition, the vapor we obtain, when we heat the liquid mixture of any composition, the vapor obtained is richer in the more volatile component. Since A is more volatile, when we heat any liquid mixture of any composition, we shall obtain vapor Y, which is vapor of the composition Y, which is richer in the more volatile component A. We are going to look at the examples, of course, but we also need to note that since liquids A and B have got different boiling points, then they can be separated by fractional distillation. And this separation is only possible when the vapor phase has a composition different from that of the boiling point of the boiling liquid mixture. All right? When the composition or when the vapor phase has got composition different from that of the boiling liquid mixture. And in this method of fractional distillation, the liquid mixture is heated to its boiling point, all right? Giving the vapor richer in a more volatile component, right? The moment we heat this liquid mixture to its boiling point, the vapor will be richer in a more volatile component than a less volatile component. And what follows is that vapor that we obtain is then condensed by cooling to give the liquid of the same composition as the vapor. And the moment you progressively repeat heating and condensing, it will give you a more volatile component as a distillate, while the less volatile component will be obtained as the residue. In other words, in this process of fractional distillation, the moment you heat these liquid mixtures, their boiling point, you're going to obtain vapor whose composition will be richer in a more volatile component. By condensing that vapor, you obtain another liquid of the same composition as vapor, which when the process continues being repeated, you will end up getting the liquid, okay, of more volatile component as a distillate, while the less volatile component will be obtained as the residue. We are going to look at that process of fractional distillation in this diagram. Okay, so let's consider the processes that will take place in the phase diagram. So I'm going to redraw it, and then I explain what takes place. You're considering the processes that take place. And here we shall have temperature. Here we shall have our mole fraction of B. Here we shall have 1. Here we shall have 0. But I told that it can be composition. Okay, it can be composition. They can give you composition. And so what will take place if we have, of course, here we had said boiling point of pure A, B. We've said that if we have it like this, so this is the boiling point of pure A. No, pure B, sorry. And this is the boiling point of pure A. This is the vapor phase. And this is the liquid phase. Now, here I'm going to have maybe L1. T1. V1. L2. T2. V2. And have something simplified like that. You have to show the phases, vapor phase, you have to show the liquid phase. Now, this one clearly tells you that when a liquid mixture of composition L1 is heated, it boils at a temperature T1, producing vapor V1, which is richer in component A because component A is more volatile compared to composition of liquid mixture A1. So then, on condensing this vapor V1, a liquid L2 of the same composition as that vapor V1 is obtained. Okay? Liquid L2, when heated, it will boil at temperature T2, producing vapor V2, still which is more, or which is richer in a more volatile component A. So hence, you can realize that even by cooling this, you get L3. Once heated, it will boil at T3, producing V3, richer in a more volatile component. So you realize that progressive heating and condensation results into obtaining pure A as a distillate and pure B as a residue. So let me summarize the process so that you can easily get it well. So we say that when a liquid mixture of composition L1 is heated. It boils at a temperature T1 degrees Celsius to give a vapor V1, which is richer in component A compared to liquid mixture L1. Now, when we heat L1, it boils at T1 to give V1. That is the first step. 2, on condensing that vapor, V1, when V1 is condensed, a liquid L2 is obtained. A liquid L2, a liquid mixture, call it a liquid mixture, L2, with the same composition, with the same composition as that of V1, as that of vapor V1 is obtained. In other words, when you condense V1, you get L2, but this L2 has the same composition as vapor V1 is obtained. Then now we heat that V1, we heat that liquid 2. So we shall say heating a liquid mixture L2 results into its boiling at temperature T2 degrees Celsius to give a vapor V2, it gives a vapor V2 much richer in the more volatile component. So we shall realize that progressive heating and condensation results into obtaining pure air as the distillate and pure B as the residue. Remember, we said that a liquid mixture, when heated at any composition, the vapor obtained should be richer in a more volatile component. Even though they say that 70% maybe of, if they say like 30% of B was heated, okay? Even though they say that 30% of B was heated, you have to be very, 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 very smart. You have to be very, very, very smart. I'm assuming that actually another thing you need to note that these ones, they do not these ideal solutions, they don't produce azeotropic mixtures. So unlike non-ideal solutions, as we are going to see. So here we expect the pure to be either A or B, depending on their composition. Okay. Now, let me bring in a different case and then see. Because you can plot, and after plotting, they say that maybe explain, okay? They can say that maybe you explain how mixtures maybe containing like 40% of B can be fractionally distilled. 40% of B. If they say 40% of B, let's now assume a figure and we see how we can explain it. Let's assume a figure and we see how we can explain it. Let's assume a figure and we see how we can explain it. So if you have now let me draw something different, because you may not necessarily draw what you may not necessarily have a question of what exactly I've talked about. So I'm calling this one boiling point of pure B. Should always write full statements of pure B. And here is the boiling point of pure A. So this is temperature in degrees Celsius. And this is composition. Let me say composition. It will always depend on what they have given. Okay, if they give you mole fraction, you're going to use mole fraction. But if it is composition now, it means that here would be maybe 0% of A, and here would be 100% of A. Then it means that here, if from this side it would be 0% B, that is if at all you're given composition, and here you'll be having 100% of B. But this composition here should not worry you. Otherwise, you can be given mole fractions and then they give you percentage. You distill the percentage. So still, there is no big deal. If you're given mole fractions, you can deal with mole fractions. But when they say fractional distill at 40%, where you have 0.4, maybe that is where you would start from as your 40%. Okay, so it can be given as mole fraction or as a percentage. All right, so here, boiling point of B, boiling point of that. So this is vapor phase. And this is liquid phase down. The vapor phase, liquid phase. Now, in this question, they can say maybe when, they can say explain the process that takes place when a liquid containing 70% of A is heated. If they say 70% of A, you come at 70. This is 70% A. But if otherwise, they can say 30% of B. You come now this side, you look for the 30% of B, and you start from there. But if they say 70% of A, remember we said that at any composition, when the liquid mixture is heated, you obtain vapor richer in the more volatile component. So we shall be going this side, because the more volatile component is B. So if a composition of 70 is heated, it will boil at a temperature. It will boil at a temperature T1, but we'll give a vapor because it's the vapor curve. So the vapors are going to be obtained here. So this is the vapor curve. So if you hit 70% of A, it will boil at T1, giving vapor V1, which vapor will be richer in B because B is the less volatile in this case. Remember, I told you that here you can be given more fractions, but they say maybe 70% of that. So still at 0.7, that is where you have your 70%. Now, then condensing this vapor will give you a certain liquid, maybe L1, okay? Which when boiled will boil at T2, producing vapor V2, which when this vapor is condensed to give liquid L2, repeated processes will get you the distillate as B and the residue as A, as simple as that. Now, so when you're explaining this process here, you will say that maybe when a liquid containing 70% A, or it can be 30% B, is heated, it will boil at a temperature T1 to form vapor of composition V1 containing a higher proportion of more volatile component B. Why do we say B is a more volatile component? It has a lower boiling point, meaning that much of it escapes to vapor phase easily. So when that vapor, that is the first bullet, when the vapor is condensed, it forms a liquid mixture L1, but of the same composition. Of the same composition as vapor, V1. Now, when liquid L1 is heated, it boils, of course, at a temperature T2 degrees Celsius to form a vapor of composition V2 containing a higher proportion of more volatile component B, more volatile component B. All these are max volatile component B. Now, when that vapor V2 is condensed, still you continue writing. Let me read it because of my space. When this vapor V2 is condensed, it forms liquid L2 of the same composition as vapor. Repeated vaporization and condensation, or repeated heating and condensation will yield pure B as a distillate and pure A as a residue. You need to know that. When vapor V2 is condensed, that is what you have to add here. When vapor V2 is condensed, it forms liquid L2 of the same composition as the vapor. Repeated heating and condensing will yield pure B as a distillate and pure A as a residue. So that is what clearly you have to know to be very, very, very safe in explaining these phase diagrams, especially the boiling point composition diagram. Now, allow me, before I give you a guiding question, allow me briefly describe for you the process of fractional distillation. Fractional distillation using the fractionating column. Fractional distillation using the fractionating column. Now, basically here, when a liquid mixture of a given composition is heated, we say that the vapor richer in a more volatile component, now in this case is the one that ascends the fractionating column, okay? When it is heated, the one which is richer in a more volatile component is the one which ascends the fractionating column. In other words, let me sketch something small. It's just a sketch. I'm going to explain using this sketch. Then the words I'll be mentioning, one can write them as an explanation. It's just a sketch. So here is my fractionating column. Let it be on the same level with this. So this is the liquid mixture, maybe of A and B. Liquid mixture. And then this is the distillate. And then here is my liquid condenser. This is my Rabi condenser. This is my fractionating column. Fractionating column packed with glass beads. And this is my thermometer to measure the boiling point. Thermometer. So now what we are saying that when a liquid mixture of a given composition is heated, the vapor richer in a more volatile component will ascend to the fractionating column. As it is being cooled by the large surface area provided by these glass beads. These are glass beads. The fractionating column are glass beads are responsible for cooling because of the large surface area they provide. So this one will result into the formation of a liquid that ascends the column. Now, the descending liquid comes into contact with the more ascending vapor, and at each point in the column, an equilibrium is established. Remember, here we are saying that the liquid which is more volatile ascends to the fractionating column and gets cooled by the large surface area provided by the beads, resulting in formation of the liquid that descends the column. Now, the descending liquid will form an equilibrium, or will be in equilibrium with the ascending liquid, or rather with the ascending. There is an establishment of equilibrium between the liquid vapor and between the liquid and the vapor. Thus, boiling will take place. Now, this will result into formation of the vapor as boiling takes place. Vapor will be formed that is richer in more volatile component at the top of the column, which condenses within the Rabi condenser and collected as a distillate. So in other words, the process is when a liquid mix of a given composition is heated, a vapor richer in more volatile component ascends the fractionating column as it is being cooled by the surface area or by the larger surface area provided by the glass beads in the column, resulting into the formation of a liquid that descends the column. The descending liquid comes into contact with the more ascending vapor, and at each point in the column, an equilibrium is established between the liquid and vapor. Thus, boiling takes place. This results into the formation of the vapor that is richer in a more volatile component at the top of the column that condenses in the Rabi condenser and is collected as a distillate. So that is the process that one can give in case we have to talk about the fractional distillation using the fractionating column. We have applications of fractional distillation. It is used in the purification. We can use it in the purification of crude oil, can use it in obtaining nitrogen and oxygen from liquid air, can use it in determining concentration of alcohols in breweries, all right? Something like that. And it works on a principle that at any given point in the fractionating column, the ascending vapor is in equilibrium with the descending vapor, rather with the descending liquid. The ascending vapor is in equilibrium with the descending liquid. Also, that the vapor in a fractionating column becomes progressively richer in a more volatile component. So those are two principles it can work upon. That at any point in the fractionating column, the ascending vapor is in equilibrium with the descending liquid, and that in the fractionating column, the vapor becomes progressively richer in a more volatile component than the less volatile component. So I'm going to give guiding questions to all viewers to do. One, the table below shows how vapor pressure of mixture A and B varies with the mole fraction of A at a certain temperature. The mixture of A and B is assumed to be ideal mole fraction of A, XA, then total vapor pressure of the mixture in atmospheres, 0.0308, 0.2, 0.4, 0.6, 0.8, 1.0. 308, 318, 328, 338, 348, 358. A, plot a graph of vapor pressure against mole fraction of A. B, from the graph, determine the uncirculated vapor pressures of A and B. 2, partial vapor pressure of A and B when mole fraction of B is 0.3. 3, mole fraction of A at which the partial vapor pressures of A and B are the same. And C, sketch the boiling point composition diagram for this mixture and briefly explain how the mixture containing 40% of B can be fractionally distilled. That's number 1. I had prepared 2 questions. I had 2 questions. In the other lesson, I'll first do the corrections of these ones because I need us to understand the technicalities behind this question. So in our next lesson, I'll first do the corrections, then we progress. Number 2. Compound A, boiling point 372 degrees Celsius. And B, boiling point 399 degrees Celsius. Form an ideal solution. A, sketch a labeled boiling point composition diagram for the mixture. B, using the diagram, describe how pure A and B can be obtained from the mixture containing 50% of B. 50% of B. Feel like giving you the final question. Let me give you the final question 3. But a state 3 properties of an ideal solution. To the vapor pressure composition diagram of an ideal solution of liquids A and B is shown below. A straight line, make it a straight line. Members, make this a straight line. Mole fraction of B. P to R. This is S, T, P to R. Roman 1. Identify lines P to R and points S and T. In Roman 2, draw a fully labeled point, a fully labeled boiling point composition, boiling point composition diagram for a mixture of A and B, then Roman 3, state what will be obtained as a distillate, what will be obtained as a distillate, and residue if a liquid mixture containing 40% of A is fractionally distilled. Then finally, part C. Briefly describe what takes place during fractional distillation. Part C is different from this. This one will be from the graph, but this is what takes place during fractional distillation, like the process of fractional distillation. That is what they want you to explain. So those are the questions I want you to go through. We shall have time and go through them. I wish you all the best. Stay blessed.